Well, hello. I'm going to show you a short video here that tries to describe how we define the concept of electric potential in terms of electric potential energy. Now, I assume by now you've heard a description of what electric potential energy is, and usually that's described in similar terms to how we describe gravitational potential energy. A lot of people are more familiar with that. You have some concept of that, and so it makes it a nice starting point for describing electric potential energy. But despite the similarity in the names, potential and potential energy are not the same thing. So I've got this image here that's going to try to describe the difference between them. So I just want you to imagine we take a little test charge here, and that's what's indicated in this little figure, test charge. It's a 10 nanocoulomb charge. Now, the idea of a test charge is it's so small that it has no effect on the other charges around it, but it allows us to feel the presence of an electric field. So I don't know if you can imagine taking that little 10 nanocoulomb test charge and moving it upwards from position A to position B. Because you're getting closer to more positive charges than negative, I would have a sense that you'd feel some repulsion in that. And anytime you feel that repulsive force as you move it, you feel like you're doing work against that field. And that tends to raise the potential energy of your system. This is just like if you were to grab your book and raise it upward through Earth's gravitational field, you would do work with your hand against the gravity, and you would say that you feel like you're putting potential energy into the book or into the book and Earth system more formally. So that's what we're doing here. So imagine in doing that, we have just enough charges that takes 3 microjoules of energy and gives it into the system. So that's how much work you do, and that's how much the potential energy of that little test charge would raise. So that's the idea of potential energy. Well, now let's divide out the size of the test charge. So in other words, we're going to take the potential energy in that movement from A to B, and we're going to divide it by the magnitude of the test charge itself. And so if you take 3 microjoules and divide it by 10 nanocoulombs, you get a value of 300. So what we do with electric potential is we describe not what we're doing to a test charge, but it's actually a characteristic of those 5 fixed charges. And what we say is the atmosphere around them have these different potential values. The closer you get to positives, the higher the potential value is. And the closer you get to negatives, the lower, or sometimes more negative, the potential value is. We define that potential as being 0 if you're infinitely far away. That means you're not close to anything. So we can go above that if we get close to positives, below that if we get close to negatives. So in this atmosphere around these 5 charges, we would say we have 300 volts, that's another name for joules per coulomb, 300 volts more potential at position B than we have at position A. And that is what we describe as the difference in potential between those 2 locations. So you see how we've divided out completely any effect of which test charge we use. If we had used a 20 nanocoulomb test charge, then we would have had 6 microjoules of energy increase in moving from A to B, because the size of that test charge certainly determines how much work you're going to have to do against the field. It's no different than trying to move 2 books up through Earth's gravity. You're going to feel like you're doing twice as much work. Well, if you divide out the 20 nanocoulombs from that 6 microjoules, you still get 300 joules per coulomb of difference between position A and position B. And that's why potential is so nice. It has no impact whatsoever if we change that test charge that we imagine moving. So that is what we do with potential energy. A lot of times we're dealing with just a single point charge. And so you should have seen potential energies being described for single point charges. We describe it this way. The potential energy is equal to K times the test charge that we're moving divided by what we call charge 1. That's the one there in the middle. They've called the test charge here Q2. And that's divided by how much distance you have in between those two charges. So the greater the distance, the less potential energy. So in this situation, if we divide out the test charge, then we get a measure of the potential of that point charge. So this is K, Q1 over R. And what it does is allows you to describe the potential at any location around that red positive charge. It has no connection at all with Q2, which is what we described our test charge here. So in this situation, as we move from position A to position B, you see how we're getting farther away from the charge. So we're increasing the denominator here, and an increase there is going to tend to decrease the potential. So you can see we would have a smaller positive number out there at position B than we had at position A. So that's the idea of how we describe potential in terms of potential energy. And then you can look at more videos or continue on in your reading to see what this means for special situations, such as potentials within a parallel plate capacitor or potentials around solid or hollow spheres of charge. Those are some videos that I also have available. Hopefully this was enough to get you the main concept. We can go from there.